Hello everyone, I'm Richard Ding from Baidu. Today my topic is Baidu AI infrastructure. Here is agenda, 5 parts. First, I will analyze the trend of the AI compute and see why we need a system view. Then I will share the high-level architecture of Baidu AI infrastructure. And then I will share Baidu AI Computer XMen designs and roadmap and how we support the OAI project. Then I will share the example how we use our XMen to solve the 10 terabyte sparse model challenges. And finally, the summary. Okay, as we know, the data, algorithms, and compute are three key factors that driving the AI forward. So generally, the bigger data sets helps increase the accuracy, and these years algorithms is becoming more and more complicated with more parameters. So this has raised bigger requirements on the computer performance. Yeah, luckily the AI computer performance has increased almost 50 times during the last years. So and also we have more options. At the same time, the memory capacity of the accelerators increased a lot, so that it can support bigger models. But that is still far more not enough for the terabyte sparse models. As the performance of the AI accelerators increase, the power consumption also increased a lot. So that has bigger challenges on the power and thermal designs. Okay, so for the networking, so the interload communication bandwidth has increased almost 10 times. So it is changed from the traditional PCIe to the high bandwidth NVLink switch. And for the interload communication bandwidth, it increased about 5 times. So it can support 200 gig RDMA connections, but that is still far less than the NVLink switch connections. So our strategy is should be try to first scale up and then scale out. Okay, so for the AI computing, we try to map in the sorter flow to the hardware system designs. So for the sorter flow, it has six parts. So for the data loading, that has dependency on the distributed data I/O systems, and for the pre-processing, that has dependencies on the CPU and the memory capabilities. And then sending the data from the CPU to the GPUs, that has dependency on the uplink bandwidth. And then in the forward and backward, so this has requirements on the performance of the AI accelerator itself, and also the memory bandwidth and capacities. And then for the distributed trainings, there's a lot of gradient synchronizations, so that it has dependency on the networking, the collection within the AI accelerators within the load, and also the communication bandwidth between the load. So basically, this system has 4 challenges. So the compute, storage, communications, and also scalabilities. So that is should be scalable to support different workload and also support very larger data sets and data sets models. So the system is very complex. Maybe one sorter factors changes, then the bottleneck of the system can be changed. So we need a system views. Okay, here is the high-level architecture of Baidu AI infrastructures. So basically, it has 7 layers. So for the AI chip, currently we mainly use GPUs, but also Baidu has been building our own AI chip, Baidu Kunren. So for the system designs, we have the AI Computer XMen. Also, we have storage and interconnecting systems. Besides the hardware, we need a lot of software optimizations to make sure the software can fully utilize the hardware capabilities. And then in the cluster, so we build our cluster based on the Kubernetes. So it's a cloud-native solutions. And it also has a smart scheduler that is able to be aware of the hardware topologies. and also it can support elastic scalings that can be very efficient for the distributed trainings and also can be fault tolerant. And then we build several platforms based on the clusters. That is development, training, and serving platforms to cover different stages of the AI development, AI development systems. And then it's a framework. So we on our system, on our platform, we can support different frameworks, but Baidu own deep learning framework Paddle is widely used internally. And then we can support different applications. Yeah, besides the traditional the vision, speech, and NLP, we are also able to support the sparse models like the CTR and the recommendations. So basically, we can say that Baidu AI infrastructures, it covers the AI chip and to the system designs, clusters, and even now to the deep learning frameworks. Okay, today I will share more about the AI Computer XMen. Yes, here is the roadmap. It already has 4 generations. Each generation has its unique design concepts. So the first generation was launched the second quarter of the 2016. At that time, it has the highest density in the world. And then the second generation is the first one to support liquid cooling. And the third generations adopt a modular design so that it can be updated to support other solutions very easily. And our first generation, the latest generations, is OI compatible. That is built on the OI ecosystems. Our first generation XMen is able to support 16 GPU per box, and it is able to scalable to 64 GPUs. So it basically has two very big parallel design concepts. One is the hardware disaggregations. In our designs, the CPU and actually the GPU are physically disaggregated from each other. So all the space of the GPU box is able to support the GPU itself, so that it can help to achieve the high densities. And the other one is that we use the ring or reduce algorithms to avoid the limitation of the P2P capabilities in the GPU drivers. So the ring or reduce only need to make sure that the agents in the GPU need to communicate with each others. So together, these two pioneering design concepts helps great for the 16 GPU per box to work. And these two design concepts are also used on our next generation's XMens. And our second generation is upgraded from the PCIe to support NVLink, and also it has very flexible I/O interface. So this is quite different from the NVIDIA reference designs. We can support different numbers of leak cards and NVMe drives in the systems. And the system supports the liquid cooling and the air coolings. Liquid cooling is very important to make sure the AI accelerator performance can increase later in the futures. That can help achieve the highly cooling efficiencies. And the third generation adopts a modular designs. So it is upgraded to support the fully connected NVLink switch, and also it adopts 48 watt powers. It has flexible topologies. So this system is designed to is very a modular way, so that any component of the system can be upgraded very easily, and also it's able to support different accelerators. And to make sure the performance of the AI accelerators can be fully utilized, so we upgrade our XMen DOS3. So the CPU load is upgraded from 2 socket to 4 socket. So this system can make sure all the performance of the GPUs can be fully utilized. So this is the first 4 socket AI computer in the industries. And the fourth generation, XMen 4.0, this is built based on the OI ecosystems, and also it supports liquid coolings. Yeah, Baidu has been actively working in the OI project, and luckily this project already get a great support from the bigger communities. And Baidu is also committed to build our next generation based on the OI standards. Okay, our Baidu AI Computer XMen has been widely used for the traditional deep learning use case, like the NLP speech vision use scenarios. But for the sparse models in the CTR recommendations, yeah, currently in the industry, CPU solutions are used. So it's very because it's very challenging to use the GPUs. Yeah, here is the why it is challenging. Okay, so for the sparse models, yeah, it has in our system it has a billion samples. So for each samples, it has dense features and also sparse features. So it needs to extract the features. So it is compute bound, and the sparse models has a very big embedding tables. In our case, it's almost 10 terabytes. So this has bigger requirements on the storage capacity and also performance. And then we need to translate the sparse input to the dense input. So in this stage it is compute bound. And for the trainings, it has need to synchronize a lot of sparse features. So that has big requirement on the communications. So basically, we can see that for the sparse models, yeah, it has a lot of engineering challenges. It is it requires the communication, the compute, the storage, and also the communications. So it covers three aspects of the computing architectures. And so we try to solve these problems, use the GPU architectures, use AI acceleration architectures. So we adopt a hardware-software co-design architecture. So it has 4 layers. So the lower one is AI Computer XMen, and that is highly customized for the sparse models. And then is our distributed training platform Commin. And then is the AI box software solutions that try to make good use of the hardware capabilities and the platform capabilities to try to solve the CTR and recommendation challenges. Okay, our XMen is highly tailored for the sparse models. It tries to solve the storage, compute, and communication challenges. So the blue part, the memory, the SSD port, and the GPU memory are trying to solve the storage I/O problems. The CPU memory, the CPU port, and the GPU, the black part, are designed to solve the compute problems. The link port and the NVLink, these green parts, are designed to solve the communication problems. So we can see that every component of the AI Computer XMen is specially designed to solve specific problems in the sparse models. And this system is very flexible. Yeah, first, the CPU and the GPU actually are physically disaggregated, so each part can be upgraded very easily. And second, the system is also able to support multi-load connections, so that it can be designed to support bigger models and bigger data sets for the distributed trainings. Okay, I will share how we solve the storage, the compute, and the communication challenges. Okay, the biggest challenges for the sparse models is how we can store the 10 terabyte sparse models, and also make sure the performance is good. So we use 3-tier hierarchical solutions. The SSD primed server is able to support 10 terabyte sparse models. That is solve the capacity problems. And the CPU memory, the primed server, can support 1 terabyte parameters. That is to solve the performance of the cache, or to solve the performance problems. And then the HBM primed server, 0 100 gig memories, Yeah, it's used to store several batch parameters. So that is used to accelerate the trainings. So basically, these systems adopt a three-layer hierarchical storage to achieve a good balance of the capacity, the performance, and the cost. And also, we adopt a distributed SSD parameter servers, so that can to support even bigger models. And then for the compute, when we try to use one GPU load to replace more than 100 CPU load, the second challenge is the big CPU shortage, because actually for the sparse models, the matrix compute actually is less than 30%, so the CPU is very short. So we also upgrade our hardware system from 2-socket CPU to 4-socket CPU, so that can help somehow solve the CPU shortage, but that is still not enough. Okay, we also offload a lot of operations from the CPU to the GPUs, and we also try to make good use of the GPU capabilities for its communication, for its memory, and for its compute. So we design the HBM parameter servers. So on the picture, we can see that each GPU is able to access each other with very high-speed P2P capabilities, and also the sparse parameters are stored in the HBM memory. So that is very high bandwidth memories, and also the communication between the GPU is quite bigger than that between the CPU and the GPUs. So we make good use of the GPU capabilities. So together we can solve these compute challenges. And then is the communications. So for the sparse models, it has two features. One is the dense features, the other is the sparse features. So for the dense features, it still uses traditional ring-reduce algorithms. Yeah, basically the high cube mesh topology is okay. But for the sparse features, because we use distributed GPU parameter servers, so the parameters can be located on either GPUs. So the pattern is a random peer-to-peer access. So in this case, we need to make sure each GPU can be accessed to each other at very high speed and with lower latencies. So in our designs, we used the fully collected NVLink switch to support the sparse model peer-to-peer access. So this is very important for the sparse models. So basically, we can see that we use the SSD to solve the storage problems. We use the 4-socket server to solve the compute problems, and we use the fully collected NVLink switch and to solve the communication problems. And that is basically for the single load capabilities. But we still also need to support distributed trainings to support bigger models and bigger data sets. So we designed the system for the server load communication capability for the GDRs, the better scalabilities. Yeah, in the traditional way, the communication will involve the CPUs. So as we said, the CPU in our system is already a very big bottleneck. So we need to offload all the activities to some other parts. So we use the GPU direct. So in that case, no CPU environment is needed. We use a server link cars to do that. So that can help to achieve better scalabilities. Okay, now the summary. Yes, Baidu has been building our 4 AI infrastructures from the AI chip Kunnan, AI Computer XMen, the AI training platform Commin, and to the deep learning framework Paddles. So we have the four stack solutions. Yeah, we use that to support diversified AI workloads, including the vision, speech, NLP, and also the CTR and recommendations. And Baidu is actively participating in the OI project, and also we are committed to build our XMen next generation XMen based on OI ecosystems. Yeah, um, Baidu AI Box is able to train 10 terabyte sparse models with a single XMen, and also can be scaled to support bigger models and even bigger samples. So we have more details at our papers at SysML. Yeah, SysML is a conference that targets the machine learning and systems. So you can more details in that. And AI box is very good examples for the OI fully collected topologies. So we can use the fully collected the capabilities to solve the sparse model challenges very efficiently. Okay, that's all. Thank you.
Yeah, during the presentation, there is one question for XMen 2.0 is air cooling while rack level. Yes, our AI computer XMen is a rack level design. The rack design is quite similar like OCP rack. Yeah. Okay, the second question, how much of the work is going on at the San Jose, California lab? The whole design is done at Beijing, so not too much work from our San Jose R&D center. Yeah, all the work is done at Beijing. Okay, last question. What are the CPU requirements for the GPU Direct? GPU Direct actually, okay, so to make GPU Direct work, the GPU and the link card should be located on the same PCI switch. So in this design, generally the CPU would require more PCIe lanes. But in our design, we put the link card, the GPU Direct RDMA link card on our GPU box. So the GPU and the link card actually are located on the same PCI switch. So in this case, it's okay. But we also because we need to connect more links between the CPU and the GPU. So we need to try to avoid the QPI path. Otherwise, the GPU Direct RDMA cannot work. Yeah. Next question. What do you use for PCI fabric? Yeah, the PCI fabric actually is built on the PCI switch capabilities. Currently, like the Broadcom and microchip or the previous micro-semi PCI switch actually supports PCI fabric capabilities. We build on our solution on the Broadcom solution. And also the PCI fabric is helpful to avoid any QPI limitation to enable the GPU Direct RDMA. Yeah, for example, in NVIDIA reference design in their HGX1 or HGX2, generally it supports 4 or 8 link cards. So their PCI switch is connected to the CPU through different uplinks. So in that case, it's quite possible there is a QPI limitation. So generally, you need to have a balanced link card. In our case, we have a 2-layer PCI switch and also the PCI fabric capabilities. We could use 1 card or 2 card. Yeah, the number of the card is very You can choose any number of the link cards, but you can still keep the GPU Direct work. Yeah, this is very flexible. Okay, next question. Is the PCI fabric torus, or what is the connectivity? Yeah, there's no details on the slides. Generally, there are two-level PCI switch. The lower level is a two PCI switch, and the upper level is one. I think, yeah, maybe there's one slide mentioning that. Yeah, it's not torus. For one box, with 8 GPU, it has 3 PCI switch. Yeah, so it's not torus. It's just a two-layer PCI switch. Okay, thank you.